all the way out to times probability we get ahead on flip 5. But each of these is the same probability of 1/2. What's the chance I got ahead on flip 1? That's 1/2. I could have got ahead or tails, and they're equally likely. Same can be said of getting ahead on flip 2, or 3, or 4, or 5. And here I did write these 1/2s come from the 3 and 4 that I concatenated there. This is 1/2 to the 5th power. And what does this kind of stand for? Well, I had to get ahead on flip 1. If I didn't get ahead on flip 1, I'm automatically out of the event. I don't even need to keep looking, right? So if you were asking, I have a sequence of coin flips, does it satisfy the event, got all heads? I can look at flip 1, and if flip 1's a tail, I don't even have to look at the other 4. It's know that you didn't get all heads if flip 1 was a tail. So the first event has to succeed. I had to get ahead on flip 1. That happens with probability 1/2. And also head on flip 2, and also, so each time that I multiply by another probability by another 1/2, I shrink the likelihood of staying inside the event. This becomes 1/2 to the 5th, or I can distribute that power. 1/2 to the 5th is 1/32. We get the same answer. And especially if I hadn't, gone through and written this out so carefully and explained so much, this would have been, I think, a bit faster than going through this analysis, at least at this point. So we could have gotten the same answer. As kind of a side note, recall the distributive property. We have, in a sense, two distributive properties for distributing the probability operator over these conjunctions and or. But just as a side note, recall how to spell recall. Recall that we have a distributive property, the kind of standard one, a times b plus c equals ab plus ac. We also have a distributive property for exponents that ab to the c power equals a to the c, b to the c, or similarly, a over b to the c power equals a to the c over b to the c. So distributive property for PEMDAS, parentheses, exponents, or roots. Roots, like square roots, are just exponents. Multiplication, division, addition, subtraction. The distributive property takes us one level down on the PEMDAS chart. So multiplication, division, distribute into addition and subtraction. Exponents, they have a little funky distributive property. They right distribute but not left distribute, but they distribute into multiplication and division, like this. So just remember that from algebra. That is something that will come up often in the course. As an aside, at one point in the past, I had as heated of a debate as debates get in between math folks about whether exponents technically distribute into multiplication and division, whether that's technically a distributive law. And needless to say, it is a distributive law. The concept of distributive law is much more general than just this idea here, right? It applies to exponents distributing into products or quotients. It also applies to probability operators distributing over conjunctions like and or. So the concept of a distributive law, we abstract away from this detail. Again, that's very much the power of mathematics, is we say, hey, I know how a times b plus c works. I can abstract away from that. Interestingly, we actually call this abstract algebra, is literally the field that it's called, but we abstract away from this specific algebraic statement to a much broader class of statements that we call distributive laws for things like this, or also for logical distributive laws related to probabilities and so on. Okay. There are also distributive laws for things like A and B or C. So like, events that are more complicated. These also have a set of distributive laws that go with them, but that's outside the scope of what we're talking about. Yeah, somebody raised their hand. Question.
Yeah, I was curious, and maybe I'm off here, but I'm imagining, like, say I have a convenience store and I have 5 slot machines inside.
Mm-hmm.
Would each handle spin be counted as a separate event? Like if I wanted to calculate, say from the perspective of the player, and they're asking, how likely am I to win? And then from the perspective of the owner, where I'm like, how often do my machines pay out? Like, are they the same question, or?
Yeah, so if you, I'm going to answer this like, I guess it becomes a little bit complicated what you mean by a slot machine. So there are slot machines that are calibrated to guarantee certain payout rates, and I think that's how the modern ones work. Is like, before you even pulled the hand to what decided, the next pull is going to be the jackpot winner, or the next pull is going to be a loser, or something like that, roughly speaking, so that they can guarantee that they're in compliance with the regulatory commissions that say you have to pay out this percentage of the money that's put in. But let's just suppose that like it was basically just like a roulette wheel kind of thing. Like you pull the lever and some mechanical doodads, just springs and things like that, just spin the things, and the machine, the owner of the machine, the player, nobody knows in advance whether it's going to pay out or not. So that it's like a die roll or something like that. Let's suppose that that's the situation that we're looking at. This gets a little bit into the philosophy of Bayesianism versus frequentism, maybe, but at least from the perspective of the player and probably from the owner, they have no idea whether that handle pull is going to be the jackpot winner or loser or something in between. So from that perspective, from the perspective of degree of belief being what probability is representing, that's a true statement. In that kind of a situation, it actually wouldn't matter whether you have 5 machines and you do 1 pull on each machine, or whether you have 1 machine and you do 5 pulls on that machine, or you do 2 pulls on machine 1 and 3 pulls on machine 4. Each of those pulls would be independent events, because if, again, in this structure that I described to you, if I know that machine 1 just paid out the jackpot, that machine 1 could pay out the jackpot twice in a row. Now, again, like the modern versions with electronics and all of that kind of stuff controlling all of this, I don't know how that works. I don't know if it's like, hey, I just paid out the jackpot, I'm not allowed to pay out the jackpot for another 1,000 spins. I don't know how that works. But yeah, so if we had just 5 machines that were all set up the same way, that's another assumption. Is in casinos, sometimes they set up like slot machines on the aisles that are a little bit freer, that they'll pay out a little bit more, and people walking by see people winning, and then that attracts them to the slot machines that are in the inside, and they might play those that take a little more of your money, or vice versa. The casino owners might say, hey, the ones in the aisle are going to be most likely to be played no matter what, we want to capitalize there. But anyway, if all the machines were set up the same way, and if we didn't have access to any of the electronic doodads inside to know whether, say, getting a jackpot means you can't get a jackpot for another 100 spins or something, then yeah, so every pull would be independent, whether it's 1 pull on each of the 5 machines or 5 pulls on 1 machine or whatever. Each of those pulls would be an independent event, and you would win the jackpot or lose your money or win $5 or win $1 or something. Those might be different outcomes for each of those events. And then you could say, what's the probability that I win the jackpot on 5 pulls in a row? Win 5 jackpots out of 5 pulls, that would be like probability of winning the jackpot times probability of winning a jackpot, 5 times. So whatever, you know, like 1 in 2 million times 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 1 in 2 million. Yeah, but so that's a good example. Clearly, if there were 5 different machines, we'd be a little more comfortable assuming independence than if there was one machine and we were doing 5 pools. Because again, I don't know how the internals work. I don't know if maybe if I get a jackpot, there's something on the internals that says you're not going to give out a jackpot for another at least another 100 spins or something, or maybe that's not true. I don't know. But I think with 5 different machines, I'd be more comfortable assuming independence. But I would think that even on one machine, we could probably assume independence from pool to pool. Yeah, that's a good question, though. We use a lot of casino games too when we're discussing probability, because again, they're specifically built for equal likelihood a lot of the time. Like a roulette wheel, you know, somebody has gone to great lengths to set up the roulette wheel in a way that each of the little bins is the same size and is equally likely to be chosen as any other bin. And when there are small, tiny manufacturing defects, people can actually exploit that. And there was a group of folks, I want to say they were maybe in Spain or somewhere over that way, where they developed these little computers, and they had like this little, I don't know, some kind of like mouse pad kind of thing, but it could also signal back to them in their shoes. And they would like time the ball going around the roulette wheel and time the wheel, and it could somehow feed back to them like what number they thought it was going to land on. And there were other folks who like somehow collected tons and tons of data on a whole bunch of roulette wheels and found that some of them were just slightly out of balance and were a little more likely to land on these numbers than those ones, and they exploited that. So there are all kind of people looking for these edges like this. Or, you know, there's the MIT blackjack team. They weren't looking for that kind of a thing, but they were looking for specific tables at specific times that were more amenable to playing than other tables or than average. So yeah, people use a lot of probability in casino games or in the lottery or those kind of applications. Okay, so let's look at this application. Suppose we have a hard drive that has a 2% chance of failing in any given year. We choose to back up our data onto an independent hard drive. What's the probability that both drives fail in a year? We said it's an independent hard drive, so assuming independence. The probability that both fail, well, both fail if the first one fails and the second one fails. And because we have independence, probability first one fails and second one fails is probability first one fails times probability second one fails. That's 0.02 times 0.02. That's that is 1 in 2,500. 2% is 1 in 50. 1 in 50 squared is 1 in 2,500. So if we back up our data onto an independent hard drive, our probability of both of those failing in a given year is 1 in 2,500, rather than say 1 in 50 for a single hard drive. Now this brings up an interesting question we've already touched on a little bit with the casino games example, actually. But in reality, again, when I have my nice mathematical structure, everything works the way that I say it works. But in reality, I don't get to determine the laws of nature. I have to model them. So how independent do things have to be kind of naturally for me to be comfortable applying independence? That's a tough question, right? If I have 2 hard drives just sitting on top of one another in my desk drawer, I probably don't want to, and if let's say I bought them both at the same time and they're both the same model, I probably wouldn't want to call those independent, right? I might have got 2 hard drives from the same batch and that was a bad batch that, they just fail a little sooner. There might be something that happens to my desk or my house or something, and I get a flood or whatever and destroys them both. If I'm super careful, maybe I have one hard drive and one safety deposit box at one bank and another hard drive at a different safety deposit box at a different bank. And, I might be a little bit more confident, or a lot more confident, assuming independence. But even then, it's like, well, I have the same data on both of them. What if the data is, what if I have a virus on both of them? And as soon as I plug one in, the virus says, hey, spin up and, don't turn on any of your cooling protections or whatever, and spin as fast as you can and, overheat. And then I plug in the second one and it does the same thing. So, so it's a legitimate question of it, if you as an actual person in actual reality were actually backing up important data onto hard drives, how far would you have to go to be willing to assume independence? That's a hard question to answer. But again, in the mathematical structure, if we say the hard drives are independent, then the hard drives are independent, and we can get an answer under the mathematical structure. In reality, will a 2% chance between two independent hard drives look like 1 in 2,500 chance? Probably not quite. Maybe it looks very much just like 2% chance if I have two of the same hard drive stacked on top of one another in my desk drawer. Maybe if I split them up between two different bank vaults, it looks much more like a 1 in 2,500 chance. And something intermediate behavior on my part probably gets me an intermediate probability in reality. Okay, let's look at another example here from healthcare, from clinical lab management. So here's an example or an application. It does come with a caveat that we're making a lot of assumptions here. These assumptions might not hold true for a certain test or for a certain lab. So, I mean, this is more a thought experiment. Don't go to Quest or something and say, hey, you're doing everything wrong because we did this goofy thing in stats. It's more of a thought experiment, but it's something that could be done in certain clinical settings. So clinical labs, the type of lab where you go to Quest Diagnostics, get your blood drawn, get your glucose back, or maybe you take a COVID test and they tell you whether you have COVID or not. They could maybe save money by combining patient samples to test for a given disease. So here's the idea is if I have, let's say, 10 patients, I have 10 test tubes or vials. Is that 10? 5? Yeah, 10. And maybe all that I want from this test is has the disease or doesn't have the disease for each of these. So, has the disease or doesn't have the disease. That's all that I care about, is that binary answer, has the disease, doesn't have the disease. Well, if I'm in a situation where I think that most of the people that I'm testing don't have the disease, I could take a sample of these samples. I could combine all the 10 these 10 together to make one kind of grand sample. And then I ask myself, does this test positive or negative? Provided that my assay is sufficiently sensitive, is able to pick up presence of the disease at a sufficiently low number, a sufficiently high dilution, in this case, maybe a 10-to-1 dilution from normal. Well, and if my disease that I'm looking for is fairly rare, if all of my 10 folks are negative, this pool is going to be negative. And if my test is sensitive enough that if even one person was positive, the pool would be positive. If the pool comes back negative, then I can infer that all 10 individuals in the pool are negative. So with one test, with one amount of machine time, with one amount of reagents, perhaps with less than, with some intermediate amount of tech time, some savings over this, but probably not just 1 unit of tech time, I can evaluate the whole pool of 10 people. If it's negative, I can call them all negative for, say, 1/10 of the cost of materials, maybe. When we we're really worried about materials, like during COVID, when these little like specialized pipette thingamajigs that they use in the labs or the reagents were in short supply. This might have been a much more important thing than looking for a disease in a situation where the cost or the scarcity isn't a big deal. So if all of the folks in the pool are negative, the pool is negative, and seeing that the pool is negative is sufficient to infer that all of the folks in the pool are negative. On the other hand, if we had, say, even one person amongst the 10 that was positive, then the pool would test positive. And then we could do something like we say, okay, the pool tests positive. There's at least one person in here that's positive. I don't know which one it is. So then I'll just come back and test each member of that pool individually. I don't get any savings there. In fact, there it costs me one extra amount of reagent when the pool tests positive. But if it's a fairly rare disease, I might often get a whole pool that tests negative, and I can, on balance, have a lot of savings. So one thing that I'm really interested in then is, if the disease is such that the pool is often going to test positive, this isn't a good savings. But if the disease is such that the pool is quite often going to test negative, every once in a while, I have a positive pool and I have to go back and test all the folks in the pool. But most of the time, the whole pool tests negative, and I can just give a negative result for all of those folks in the pool. Maybe that is a situation where pooling would be beneficial. Okay, so let's take a look at this. If the probability that a patient has the disease is 1 in 1,000, what's the probability that a sample of 10 patients, a pooled sample of 10 patients, will test positive? We're assuming independence here. So if these 10 patients all came from the same floor on the same hospital ward, probably not a great assumption to make. If they came from different community hospitals or different community labs, probably a pretty good assumption to make. If we had some intermediate, real world result, maybe this would be in the reasonability of this assumption would be intermediate. Not so great, not so terrible. But here we're going to make the assumption again for this thought experiment. So what does it mean for the pool of 10 to test positive? What would make the pool test positive? Well, maybe patient 1 is positive and the rest are negative, or maybe patient 4 is positive and all the others are negative, or maybe patients 3, 5, and 9 are positive and the rest negative. There's a whole bunch of ways for the pool of 10 to test positive. In other words, there's a whole bunch of ways for at least one of 10 patients to be positive. I really don't want to count all of these different ways. But I do notice that the complementary event is a lot easier. The complementary event for the pool testing positive is that the pool tests negative, or in other words, that none of the patients are positive. The probability that no patients are positive, or the probability that all patients are negative for the disease. Negative. But the probability that all patients are negative, if all the patients are negative, I can think of that as being like patient 1 is negative and patient 2 is negative and patient 3 is negative and so on. but I assumed independence. So this is just the product of the probabilities. And what's the probability that a given patient is negative? Well, that's 1 minus the probability they're positive, right? This probability is 1 minus the probability that patient 1 is positive. That's 1 minus 1 in 1,000. But that's the same probability for each of these folks. They all come from the same population. So that's just to the 10th power subtracted from 1. This is a structure that comes up fairly commonly in probability theory. This idea of 1 minus parentheses 1 minus something to a power. So what does this end up being? Let me bring up the calculator. I'm going to do one simplification here just to make things a little easier. 1 minus 1 out of 1,000, that's 1,000 out of 1,000 minus 1 out of 1,000, that's 999 out of 1,000. Just to save myself a little bit of hassle in the calculator. 1 minus parentheses 999 out of 1,000 to the power 10. That looks right. This gives me 0.00995. So this is about 0.01, right? Or it's approximately 1%. Now, what might we do here if we approach this problem naively? If I said, what's the probability that at least 1 of 10 patients test positive? I might look at this and say, well, I have 10 chances to test positive. Each one is 1 in 1,000 chance of testing positive. So could I have just done 10 out of 1,000, which is 1 out of 100, which is 1%? Could I have done that? We get, so this is an exact 1%. We get an answer that's kind of close, but we see that that's not actually the right answer. It rounds to about the right answer, but there's some nuance here, right? It turns out that this strategy, while not correct, is what in calculus we might call linear approximation. It's pretty good as long as this number is pretty small and this number is not too big. But we really don't want to rely on that. So we really ought to not do it this way. That's a little bit careless. And we ought to stick with the actual probability way, going through all the details for the calculations. Why is that? Even though we got similar answers here, well, in a different scenario, we might not, our numbers might be a little different, a probability or the number of folks that we're polling might be a little bit different. And we might end up with an answer from the naive way that's really nowhere close to the actual answer. So we don't want to go this naive route. Well, for two reasons. One, we don't want to go that route because we just don't know the right probability way to do it. We want to use our probability rules. There's no probability rule that says you can do this, but there are probability rules that say you can do each of these. Just like in algebra, we can only use the legitimate algebra steps, equation solving steps, or whatever it may be. But if we were a little more sophisticated and we said, oh, well, I mean, this is just an approximation of the long way of doing it, and hey, I got a pretty close answer, maybe I'll just use the approximation from now on. We have a kind of a dangerous level of sophistication there, because we don't understand when that approximation is going to be a good approximation and when it's going to be a bad approximation. That requires more advanced math. So we don't want to use those kind of approximations, because we don't know when they're going to be good or when they're going to frankly be terrible. So here we will, or in this class, we will always go the long way when computing these probabilities. It takes a few more minutes, but we get the correct answer without any questions. Now, what if we said, okay, I mean, pulling 10 patients together, the pool is only going to be positive 1% of the time. So 99 times out of 100, I'll be in the situation where I can use one amount of reagent and knock out 10 folks. I'll save 90% of my materials 99% of the time. And then 1% of the time, I'll say, okay, well, the pool tested positive and I just have to go and test all the 10 folks now. What if I get a little bit greedier and I say, well, could I make a bigger pool? If I pull 10 folks together and that tests tests positive 1% of the time, negative 99% of the time, could I pull together more folks and make this even more efficient, going from 10 units of reagent down to 1? Could I go from 100 units down to 1 and do that reliably? So what if I wanted to know, if I pulled together 100 folks, if I had a pool size 100, this pool is going to be positive. And again, huge caveat here. This is a thought experiment. We're assuming that the chemistry works out, that if we dilute by another order of magnitude, that we still have an assay that's sensitive enough to pick up 1 part in 100 of disease very reliably. Frankly, that's probably not true in a real setting, but we're just kind of, for the purposes of demonstrating the stats, we're assuming that that the assay can handle this dilution, which it probably in reality can't. But just to go through the numbers here, what if we tried to pull together 100 folks? That has the effect of changing this exponent to 100 from 10. All of the other stuff, we didn't change the probability that any individual person is positive or anything like that. None of the probability work here changed. We just changed the number of basically component events that we're ANDing together. So if I hit second enter, super nice little shortcut. If you want to use what you typed in previously, just second enter brings up the previous entry. This is called entry. Then I can just append a 0 to the end. And I see that for a pool of size 100, the probability that that pool tests positive is about 9.5%. Our naive method would have said 100 over 1,000, or 1 out of 10, or 10%, and we can see that 10% isn't as close to 9.5% as the previous naive approximation was. So again, we don't want to just avoid the difficult probability calculations and go some naive route to avoid the work. We should do the work, because sometimes that naive method gets us close, but sometimes it's not close enough, or sometimes it can be very far off. It can be, quite different. Okay. So we see that the probability of the pool testing positive goes up to, say, nearly 10%. And now, 1 out of 10 times, we're going to have to break the pool apart and test each of the 100 people individually. As an aside for the computer science folks, I'll go through this, just touch on this topic. But if we looked at, say, a sample of size 10, if the pool tests positive, we can even do a little bit better. In a sample of size 10, where the probability of any given person being positive is 1 in 1,000. If the pool tests positive, probably only one of those folks is going to be positive. It's not a guarantee. But if I have the pool that's positive, the pool of 10 folks that's positive, I could do an exhaustive search and just test each of the 10 people and see which one was positive. But if I make an assumption, not quite as strong as an assumption, but if I suppose that there's probably only one person who's positive, I could actually split my pool in half into 2 pools of 5 people now. This is, of course, provided that I have enough sample for each person to split again. And then probably only one of these pools is going to come up positive and the other negative. So then I can eliminate all these 5 folks. I can split this 5 into maybe 2 pools of, say, size 3 and 2. Probably only one of these is going to come up positive. Maybe this one comes up negative and this one positive. And then here I can do an exhaustive search. I can do something like a binary search to even save myself more time and more reagents, or I should say, save myself more reagents at the cost of complexity, workflow difficulty. So, I mean, at some point, at some point, the workflow and the keeping track of, what patients have been called negative and which haven't, and all that becomes very difficult. But from a computer science perspective, if we're looking for a needle in a haystack, so to speak, often say a binary search is much more efficient than an exhaustive search where we would just look at each one of the individuals or test each one of the individuals and see who's the positive one. Okay, so then moving on to dependent events. When the probability of one event is affected by the occurrence or non-occurrence of a second event, these events are said to be dependent events. So we said if the occurrence or lack of occurrence of one event does not affect the likelihood of the other, that was independent. If the occurrence or lack of occurrence of an event affects the other one, the likelihood of the other one occurring, those are dependent events. The probability for one of them occurring depends on what happened with the other one. So some examples of dependent events, maybe drawing a card from a deck, not replacing it, then drawing another card. So the first draw that I had, maybe I drew the King of Hearts or something. If I don't replace it, I cannot draw the King of Hearts from the deck again. But for that matter, if I was looking to draw, say, the 6 of clubs from the deck on the second draw, if I did draw the King of Hearts on the first draw, there's only 51 cards left and the 6 of clubs is still in there. So I have a 6 out of 51 chance of drawing it. But if I did not draw the, whatever I said, King of Hearts or something on the first draw, I could have drawn the 6 of clubs on the first draw, making it impossible to draw in the second. So if I draw and don't replace the card, then that creates a dependency between the first and second draw. What happens on the second draw is dependent in part on what happened on the first draw. Something like, say, IQ and annual salary. We might have things like this that we ask, well, wait, are these independent or dependent? We're not really sure, right? Maybe there's some link, maybe there's only a link at kind of one extreme or the other. Do we want to model it as independent or dependent? I would say if we're unsure, it's probably better to model as dependent events. Or things like a person's age and the volatility of their investments, right? Younger folks, not just because they're more risk seeking, but for good reasons, tend to take on investments that are higher volatility that also yield a higher return. Folks going into retirement, they're in a situation where their primary goal is not to grow their portfolio, but to maintain. and protect their the portfolio they have grown, they want lower volatility investments. So typically older folks are going to have lower volatility investments, younger folks higher volatility. These are probably dependent events, you know, say event A, whether a person is over 50 versus under 50, and event B, whether they have high volatility versus low volatility portfolio. And we might define that according to something like standard deviation of their investments or something like that. So these might be examples of dependent events. It almost goes without saying, but since dependent events are not independent, we cannot use the multiplication rule for independent events. So we have another idea that will allow us to adapt the multiplication rule for independent events to a scenario where we have dependent events. And let me just clean some of this up a little bit up here. Okay, so we have this other idea now, the idea of conditional probability. The conditional probability of event B in relation to A. We write that as probability, and there's an event that we're going to discuss, B vertical line A. We pronounce this vertical line as given. If you want to write it on the keyboard, it's like if that button that's above enter, that's like one of the slashes, I can never remember which one's backslash, which one's forward slash. But if you do shift and that, it gives you this like vertical line. So that's how you can draw it on the keyboard. But by hand, we just draw it as a vertical line. This is not a divided by line. It's not like probability of like B over A or something like that, or probability of B over probability of A. It's not like this. This thing, B vertical line A, B given A, is an event. It's an event that's related to both B and A, the same way that an event like A and B or A or B is a different event that's related to both component events. Now, what this means is that it's the probability that B has occurred, or that B will occur, sorry, given that A has occurred. In other words, assume that A has occurred, reevaluate your probability for B occurring under the assumption that A has occurred. So it's in a sense, a revision of our number for probability of B under the assumption that event A has occurred. Now, of course, if A and B are independent events, probability of B doesn't care whether A has occurred or not. So if they're independent, probability of B given A is just probability of B. If I tell you A has occurred, I want you to update your probability for B occurring. You're going to say, well, I don't need to update anything. They're independent. But if they're not independent, if they are dependent events, A and B, then if I tell you, hey, event A has occurred, I want you to update your probability of B in light of this new information, then you have some work to do. Then those are not the same number. When two events A and B are dependent, we have to revise our multiplication rule. And you'll notice that it looks pretty similar. For event, quote, A and B to occur, event A must occur. The outcome has to be in event A, and that happens with probability of A. The event B must also occur. The outcome must also be in event B. That, roughly speaking, happens with probability of B, but with dependent events, the probability of B is dependent on whether or not A has occurred. So we have to say probability of B given A. Why do we say probability of B given A and not like probability of B given not A, or probability of B given that A did not occur? Well, because to satisfy the constraint A and B, the outcome must be in A and also in B. If the outcome is not in A, then we are automatically outside of A and B. The outcome has to be in A in order to be in A and B. That's why we have probability of A here, and that's why we assume that A has occurred here when calculating probability of B. So let's look at an example here in the last few minutes. Okay, so suppose we run a manufacturing plant producing widgets. The term widget is just like in business, it's kind of like the variable X in math. It's just like something that we're producing. We have 4 machines. They produce widgets at the same rate. For a properly functioning machine, no machine is perfect. The probability of producing a bad widget is 4%. But one of the machines is malfunctioning. And a malfunctioning machine produces all bad widgets. We want to find the probability that a randomly selected widget is bad. So I imagine that these 4 machines produce a whole bunch of widgets. They all get kind of mixed together, put in some warehouse somewhere, and then I choose one of the widgets randomly from that warehouse, or some customer buys a random widget. What's the probability that they get a bad one? Well, there are 2 locations the widgets could come from. So the widget that I choose could have come from a properly functioning machine, or it could have come from a malfunctioning machine. The properly functioning machine could produce a good widget or a bad widget. The malfunctioning machine could, at least philosophically speaking, produce a good widget or a bad widget. Okay, so probability of getting a bad widget. Well, there are 2 ways I could get a bad widget. It could be a bad widget and have come from a properly functioning machine. Or, and I'm being careful to use brackets here to show the precedence of the and versus or. The widget could be a bad widget and have come from a malfunctioning machine. This is clearly a mutually exclusive situation. The widget, a given widget that I pick, could not simultaneously have come from a properly functioning machine and also come from a malfunctioning machine. And now I have 2 probability calculations I need to do. Probability the widget is bad and came from a properly functioning machine. Probability the widget is bad and came from a malfunctioning machine. Pretty clearly, the widget being bad is dependent on whether it came from, or the likelihood of widget being bad is dependent on whether it came from a properly functioning machine or a malfunctioning machine. Much more likely for a widget to be bad if it came from a malfunctioning machine than from a properly functioning one. And I think with only 1 minute left, I will leave this for the supplement. We'll wrap up this problem in the supplement and then continue on part 3. You stop the recording here.